guys, any favorites on here? Or should we just take them through 1 through 4? So the first one, we have m dv dt equals minus k times v. We want to integrate this thing up. So the first thing to do is your dv dt equals minus k over m. And then separate variables. So we're going to take this very literally. So you've got dv divided by v. We're going to prime them from v0 to v. It's going to be minus k over m dt. And you know, we can go ahead and do 0 to t, that doesn't matter. But it's important that there be a v0 here. So you're going to get an exponential. You take the logarithm of that, and you get a nice result. So yeah, take your time on this one. And so this was assigned, and then we wanted to take the result of this, and in fact, I better write x minus x0. So the result of this, if you integrate it, you'll get x minus x0 integral v p prime d p prime 0 to t. And that'll give you the result. So if you take these carefully, nothing can go wrong, right? It's just a question of taking your time on it. And finally, we had limit as t goes to infinity x minus x0, and that would give us the distance traveled. So if you got that completely, fine, but we can add to this. So additionally, this is a very fundamental technique of these mechanics problems. So additionally, go ahead and do the dv dt equals dv dx times dx dt, right? So this is a different integration strategy, and this is v itself, so that's v dv dx, and you'll take that into this differential equation, and you'll just get v of x, and you can use that for the total distance traveled. So we would have v dv dx, that's our dv dt, we'll divide by m equals minus k over m times v. And you see how simple that one's going to be. The v is actually going to cancel in this case. But it's still a legitimate calculation. It'll give you this same result here in the limit. And in this case, when v goes to 0, you're v minus v naught. So v minus v naught equals dot dot dot. Okay. So that's what you want to do on this problem here. Depending on how much you got, you may just have to finish this last piece. But otherwise, you could run through the whole thing. Aha, there we go. We got another. So yeah, all of these are for the next homework. I'll just try to add something to each one. So this is for next week. Reworking these. Now the second one, u of x equals a over x plus b times x. A and b are positive, x is positive. As I stated there, a, b, x are all positive. So we, placing some value on this, we want to learn to recognize these functions. Okay, if you recognize them, it's half the battle. And let's see if we get a end that writes here. So the thing to do is look at these individually. A over x is essentially 1 over x, and we know that qualitatively it looks like that. A over x. B times x is just a straight line. So it goes to the origin, so I can just draw a straight line, and now we're adding these two contributions. And where they cross is the easiest point to add because it's just double that value, right? So I add that there. And then as x goes to 0, I'm really just looking at the 1 over x. And as x gets large, this one fades away, and I'm just looking at the straight line. So this is how we recognize the nature of a function before we actually do the analysis. Now, if you know, once you have this thing here, you can say, good, I'm gonna find the local minimum, and that'll be u prime of x naught is equal to 0. And then, right, it's clearly concave up, so we know the second derivative of x naught will be positive. So u second derivative of x naught is going to be positive. And then, that's just the math, but this is a potential energy function for, say, a single point mass. And so we have, from the theory of small oscillations, that the omega, the frequency of the small oscillations, will be root u double prime of x naught divided by m. So those are the steps there. And we're gonna get a lot of practice with this because we already have. So you'll have a bunch of these in your notes already, and you might wanna look them up again. You know, where I take a function and just sketch its general behaviors based on the knowledge, you know, our little library of basic functions that we know pretty well. Okay? So that's what we wanna always be doing on this, and you won't have any problem with that one. So actually, I don't think I have anything else to add to this one.
No homework here.
So no homework here if you got it right. Otherwise, if you didn't get all the points, then you want to make sure you work through it again. Yeah, that one was pretty basic. And remember where this came from, by the way. Where did this second derivative criterion come from for the frequency? Anybody remember that? Why the omega comes up here? In other words, remember, this was what we had called the spring constant K in a previous lifetime. So this came from, so I'll just put here recall, just so you see what's going on here. We had expanded u of x. Give myself a little room. I'll erase this here. So this was for small oscillations, which we're more or less just wrapping up at the moment. But what we had was any potential energy with a local minimum can be expanded into u of x naught, u prime of x naught. Right? You see the importance of these Taylor expansions can't be overstated. X minus x naught squared, and so forth. And if you were at a local minimum, this was always 0. And if you're doing physics with a potential energy, a constant doesn't matter, right? You can add or subtract an arbitrary constant. And that's where we ended up with u of x 1/2 k now, we'll define it, x minus x naught squared. And then f of x equals minus u prime of x equals minus k x minus x naught, which is a linear Hooke's law situation, right? So, and then you keep going there for the theory of oscillations. So, right, and there's a bunch to be done here, but if you know this, if you know about this, then you can just cut to the chase if all you want is frequency small oscillations, right? You just get that second derivative, and you're already there. And just to continue this thought, we would I'll just say let y equal x minus, let y equal x minus x naught, and then I've got m y second derivative is the same as mx second derivative, but then equals minus k times y, and that of course is just your harmonic oscillator. So that was that whole progression once again, and for this problem we just wanted to take a function and cut right to this this result. Good, so that's problem number 2. Now the third one is this quadrature technique. So let's look at this third one here. Yeah. So I said to begin with 1/2 dx dt squared, oops, that squared, plus u of x equals E. So this is when you have a potential energy, you have conservation energy, and there's a general way to integrate this. This is now a first order differential equation. So you separate variables, and you'll find this in your notes, and you end up with dt equals plus or minus integral dx, we're gonna write this down carefully, 2 over m e minus u of x, close parentheses. And we're going to put a little prime here, integration variable. There's the upper boundary, we're gonna leave the lower one open, okay? So this really is t of x. And this is just a half a dozen steps of literally solving for dx and dt, okay? So yeah, now you can do a number of things with this, so I'm gonna hold on to this here for a moment. One thing you can do is what we had assigned here, which was we had u of x was c, a positive constant times x. So it looks like that. And you know, if I indicate a and negative a, and an energy level E, so that has been indicated. What that means is that U of A is equal to E, or E is equal to C times A. And that A would be the amplitude, and this is a case that can be easily integrated of an oscillation, you know, between A and negative A. So in this case, the period of oscillations is 2 times the time it takes to go from negative A to A. Okay? Because an oscillation, you go negative A to positive A and back again, instead of negative A, complete oscillation. So for that, we have 2 times negative A to A dx prime 2 over m. And at this point, I know that I have c times a minus c x square root. And then you can deal with this in a number of different ways. This is symmetric, so you could also go to it being 4 dx prime 2 over m ca minus cx. Okay, at this point, you don't have to deal with the absolute value, or you could break it up minus a to 0, 0 to a. This would come 0 to a here. And you can even keep making it dimensionless, the integral, and pull all the physics out front. What you're going to end up with is, I think it's a root of 30 to yeah, root 32a m over c. Root 32 ma divided by c. So yeah, you want to make sure you go through with that. What we're going to add to this is we're actually going to go back to here and get x of t for the free fall problem, for the vertical free fall problem. So this is the review part that you want to go over. And the relation to free fall is kind of hidden in here. But we know the potential energy for free fall would just be mgx, right? mgx. So this one's a little fiddly algebraically, but I think you'll find it interesting. So to add to the homework problem, let u of x equal mgx. And now we have to declare some boundary conditions. So this is just the free fall problem of me throwing a rock up in the air, having it fall back down. Okay. So we actually know the solution to this, right? And when we work this out, we'll have to obtain that solution. It can be algebraically a little bit fiddly, but you're going to use u of x as mgx. And what we have to declare here is what do we want the energy to be? We can have it be 1/2 mv naught squared. So that would be a situation where we're at the origin, we're throwing something up in the air with speed v naught. Okay. So let E equal 1/2 mv naught squared. But let's let that be mgh. That tells us how high the thing goes in the air, right? This is just a free fall problem. You're launching it in the air. So this might be the one you want to use in here, so you're not mixing up d squareds and stuff. So if you go into this integral with here, mgh, and we have, this gives us initial condition, you know, at x equals 0, oops, not equals 0, at x equals 0. That should be enough information for the result of our integration of this whole thing. Right, you're going to end up with t on one side. Oh, I'm sorry, I forgot to put the integral here. This is 0 to t. Yeah, so the left side here was t, right? Not dt. So that should be enough to get us a result that looks something like this. X of t equals v naught t minus 1/2 g t squared. Is that what we should get if you launch something from ground level and it flies up, comes back down? So that's what we're shooting for, and this is clearly a much more difficult way of obtaining this result than we got before. But it's a straightforward application of these principles. Later on, we'll do things that can only be done this way, or when we do the Kepler problem, at least that'll be the route we take. Okay, good. So that one I think you'll enjoy. Although it is a little fiddly there with you got the t and you got the square stuff. Monkey around. I think we have enough information there. Now the last one is with the complex numbers. And that, again, that's the kind of problem that you just need to be able to sit down at your desk and relax a bit to make sure you get the whole thing. So I'll just put up what was there. I'll tell you what the solution was. So x plus omega naught squared x equals f of t over m. And then we have c of t e to the I omega naught t integral 0 to t f of t prime over m minus I actually C sub 0 that we are going to ignore. The initial condition just means that the particle is starting at rest at the origin, so that's fine. Okay. So put down what we get here, and I can talk a bit about how to do the integration. This one you just want to do in your own good time. So our f of t is f naught e to the minus alpha t. Alpha's naught. Yeah, so first of all, you want to remember what's going on there. You've just got a force that started at t equals 0 and is decreasing exponentially. So that has some interesting limiting cases, though, because if alpha is 0, then it's just a constant force, which is what we've done before. Now, when you integrate this thing up, you want that, I'm just going to put here, that e to the minus alpha t, e to the minus I omega naught t, dt prime of all. You always go to this e to the minus, once more field, alpha minus I omega naught t. And then, you know, if you do it this way, you know that it's just a constant. Just treat it like any old number, and the integration's no problem. And then you can keep working, etc. So here's the result. You know, we had C was x dot plus I omega naught x. So we need x is the imaginary part of C divided by omega naught, right? The imaginary part is this part in the blue bracket. And here's what I get. F naught m omega naught squared plus alpha squared. After a couple of steps, e to the minus alpha t minus cos omega naught t plus alpha over omega naught sine omega naught t. Okay. So that's what will come out after you fiddle around with all the algebra. And that limit that I asked for is going to be interesting. We can see it right here. So as alpha goes to 0, this turns into a 0. So we've got an f naught over m omega naught squared. And in the bracket, we've got a 1 minus cos omega naught t. And this alpha going to 0 kills that last term as well. And this is the result we had for the constant force that we have in our lecture notes. This one here. So it's always satisfying to get a limiting case of something you had before. And if you study all those, all these problems, they're a real compendium of the techniques we've learned so far. This last one, driven oscillations, and then we went into damp-driven oscillations, which is where we are in the current lecture. I don't know, should we add something to this one? Not really. I guess we won't add anything to this one either. Yeah, just make sure. Yeah, so if you can do all 4 of these problems, and you will be able to, right, practice them, you'll be up to date reasonably. Good, so that's the plan. Any questions on that? No problems? Good. So next I have to consult with you guys on what we had in the last lecture before the exam. We had the energy, the energy resonance expression, which I'm gonna have you guys dictate to me. I roughly know it, but we derived it the other day, and we're gonna analyze it now. So we can set this up, kind of remind ourselves of everything that happened there. And then we have enough time to do a nice analysis on this thing. Okay. Well, I'll set this up. We have the damped driven oscillations, and we're doing energy resonance. Damped driven oscillations. Energy resonance. I'll have to bring another resonance demo next time. So, in fact, we might as well just set the whole thing up. So what we have is mass times acceleration equals minus kx minus bx dot. Okay. So those are all the forces acting on it. This was Hooke's law, this was the linear friction law, and then plus some f of t. Okay. That's actually where everything started. Then we did the following. Plus 2 gamma x dot plus omega naught squared x. So we brought it into this form. Because we know 2 gamma we just defined, b divided by m, omega naught squared, k divided by m. So that's how we get to that form, which is the one we're working with. And in this case, we let f of t be equal to some constant cosine omega t. So I have to differentiate between omega naught, which comes from the oscillation, say the mass on a spring, or whatever system we have, and the driving frequency omega. Okay. And what we also did, we used the complex function for this, and without changing the nomenclature, without changing the letter, we had a e to the I omega t. And then we found after the transient decays, so after the e to the minus gamma t proportional function decays, we're left with the inhomogeneous solution that x of t turns into a cos omega t plus b. And all of the physics was in that amplitude expression, of which I had one little problem finding its local maximum. So then we did energy resonance, because we had E was equal to 1/2 m dx dt squared plus 1/2 k x squared. That was the energy of the system, no longer a constant, because it's being driven, because of this driving force, no longer a constant. And we did kinetic energy, average equals potential energy average equals 1/2 of total energy. So we we averaged over the sine and cosine, and this was then, this was before the exam, and we ended up with an expression, and this would be in your notes for the energy. You guys have that? It would be at the end of last Monday. Let me see, that's a good one. Anyone have a good version of that? Because I don't want to go through the whole calculation again.
You mean the time average over one cycle?
Yep, the energy.
F naught squared over 4m squared times omega naught squared plus k over thingy, or omega naught omegas.
Yep, that's the one. Okay. Here, let's write that down and we're gonna study it. So what did we have? 1/4 F naught over m squared. I was looking at yours. What do we have here? So far so good?
Yeah.
And then what?
On the top it's m omega squared plus k.
Plus k.
And then in the bottom is parentheses omega initial squared. Minus omega squared.
The whole thing squared?
Yeah, in parentheses. Plus parentheses 2 gamma omega squared.
Good, okay, we made it. So that's what we ended up with that time, and so I think I was reasonably thorough about all that, but we ended up with this expression here. And I'll place parentheses here, just to make sure. And we want to get a simplification of this. Notice that if omega were equal to omega naught, then, you know, we have this omega naught squared as k over m, otherwise we don't, right? So we can't just say m omega squared is k. But as an approximation, we will. So we've got this function here, and this is the energy of the oscillator, and just as before, all the interest was in the amplitude. This really came from evaluating the amplitude. Really, it you know, was our amplitude squared expression, and then we did the time averages over the sines and cosines. Okay. So this is meaningful if you're looking at the system for time scales that are much longer than the actual frequencies or actual period of the oscillations. That's what the time averaging does for you. So what do you guys see here? A lot of letters, right? If we wanted to graph E as a function of omega, what would it look like? You start to analyze this thing. You can start with omega equals 0. Okay, it's gonna just be positive omegas. Omega equals 0. This is a 0. This is a 0. So E of omega equals 0. You're gonna have F naught squared 4m squared k over omega naught squared. Okay. And the k over omega naught squared is just equal to m. It's going to cancel one of these. Yeah. Okay. So you get some constant, and you're right there. That's the first thing to look at. So what happens to this as omega grows? As we turn the dial up on our omega, on our frequency generator, what happens to this function? This grows quadratically. This here, since we're starting with something, is actually going to decrease. Okay, it's growing, and this is decreasing, and this is growing. So it's kind of a complicated situation. Is it going to have a maximum?
Well, because the whole thing is squared, it's never subtracting anything from the overall bottom. It's just adding a small amount that eventually becomes relevant.
Mhm. Well, actually, this is actually decreasing. This will actually turn into 0 at omega 0. But yeah, there's nothing dangerous happening here in terms of anything literally approaching 0. So this is going to increase. We're going to see it later. What about the limit of very large omega? So we're way out here on the right on the axis here. Omega is very large. And then you have to look at it this way. You've got omega squared, but down here you have omega to the 4th. Okay, when you square this thing, this omega squared turns into positive omega to the 4th. And so if your omega is large enough, the 4th power dominates these second powers. So way the heck out here, you're going to have some kind of 1 over omega squared behavior. So this is a function that's going to have a peak. Okay. Well, what I'm going to do next is analysis of this thing, which allows us to really simplify it. Because obviously this is a pretty complicated looking thing. You can't really see the behavior that well. Okay, but that's going to change. But qualitatively, that's what we have, right? It's going to increase. This is going to increase. It's going to get smaller. And for very, very large omega, it's going to decrease again. So we're looking for a peak. Now this next analysis does some really substantial simplification, so it's a good one to have seen. So what we're going to look at the case where gamma is small. Okay, we're looking for the case where gamma is not large. And so now consider gamma to be small. And then the behavior, gamma is small, omega is close to omega naught. So remember, omega naught's essentially the resonant frequency of the thing. So we're looking at this whole thing in the vicinity of omega naught. Okay? Those are the two cases here. So then we're going to let m omega squared plus k be approximately m omega naught squared plus k. Okay, so we're close to omega, so omega squared 2 gamma omega squared is going to be approximately, 2 gamma omega naught squared. And really what controls the behavior of the whole thing is going to be this pull down, this expression down here. And what we're going to do is omega naught squared minus omega squared squared is going to be, well, first of all, it's equal to omega naught minus omega naught plus omega, right? The difference of squares, that whole thing squared. And the approximation we're going to use here is omega naught minus omega. This one we're going to say is approximately 2 omega naught. And we're going to square this. We can do this because it's this difference here that's controlling the whole behavior of the thing. Okay. And then we're going to go ahead and plug these approximations in and see what happens. Uh-oh. Okay, so now we're coming up here. We've got E, I've got a quarter, F not over M squared. Now my numerator was just going to turn into 2 m omega naught squared plus k, which is 2m omega naught squared, or I could also say 2k. I'll start with 2m omega naught squared. Then down here I have omega naught minus omega squared times 2 omega naught squared plus 2 omega naught squared gamma squared. Right, because I replaced the omega with omega naught there. Let's see if this simplifies. We've got the 2. I'm going to do a 2 over 2 here. 1 over 2. And I'm going to have f naught squared over 4 times 2 and I have 8. 8 m. Then one of those m's from here is going to be canceled against that one. So m omega naught, I'll put the 2 in here just so we see it. Okay, 2 times 2 right there. Okay, so canceled one of the m's from that one. The 4 omega naught squared, that 4 omega naught squared, that 4 omega naught squared. So f naught squared over 8m. And now I simply have 1 over omega naught minus omega squared plus gamma squared. So this is such a simplification. And leave some space in your notes you want to, implement these things. It's all on the board, right? It's all on the board. I just got an m omega naught squared right there. So this is such simplification. Let me draw this here. I'm going to replace this one and just write it clean. And we got 2 minutes to look at it. And we'll start next week off with this thing as well. But let's just have a look at it carefully. So f naught squared 8m omega naught minus omega plus gamma squared. Okay, this is clean. If you guys look it over, be sure I got the algebra right. Because this one we can graph very easily. Okay? This one has, and it depends on gamma being small. Okay? But what does this graph look like if gamma equals 0? That's a limiting case. If gamma equals 0, we've got something that diverges at omega naught, right? So if gamma equals 0, we have this. And if gamma's not equal to 0, we're going to have something like this. So we still have a bit of an analysis to do, but this is a really good exercise to see what all has been done, because it's only when our formulas are simpler that we can really grasp them. And this is about as simple as that thing could have possibly gotten. And this resonance curve here actually plays a big role in all kinds of analyses. Now if you were to dial this omega up, right, you're dialing this frequency up and you're measuring the result and it's doing exactly this. And you can, from this resonance experiment, you can then figure out what omega naught is, right? Because it's located at the peak. And you can also figure out the damping coefficient just from these data. So anyway, yeah, this is a good example of the way physicists analyze stuff and bring it into a condition that can really be grasped. Good, so we'll leave it at that. But yeah, let's start with this next time. And we'll have it in front of us, we'll do a little analysis of it. good.